So good evening, West Didsbury and everybody in Zoomland. Rather than talking about the universe and everything that's out there, this evening we're looking in the opposite direction. We're looking at the weird world of the very, very small. So I'll be starting with just a couple of slides giving a sense of scale to get us down to the sort of scale at which the world starts to behave very differently than the world we're used to. I'll again spend a couple of slides just talking about how we figure out what the world is made of by thinking, amongst other things, about a sense of symmetry. And most of the talk will be about looking at the quantum world. And we'll finish with a few images of atoms. So we're used to the world around us being perceived on a scale that we can make sense of, being humans a couple of meters or so in height. We're used to looking at the world on a scale of millimeters to meters, perhaps to kilometers. So we're familiar with objects at the millimeter scale, and perhaps we can see objects as small as this. Some of you might recognize this. This is a pollen grain, and they might be of order a 10th or a 20th of a millimeter in diameter, or 50 microns, a micron being 1,000th of a millimeter. But that's pretty much the smallest thing we can see. We can certainly manufacture objects on smaller scales. For instance, we can make cogwheels on scales of essentially microns to tens of microns up to perhaps hundreds of microns. So these are barely visible and are only visible in microscopes, in this case an electron microscope. But of course we can really push the limit of small-scale manufacture, not in terms of mechanical objects, but in terms of electronics. Things that we can etch into the surface of silicon, essentially. So if we think of a microprocessor, which is probably in the heart of this computer I'm using, or the laptop on which you're using to display the Zoom call, the microprocessor might have an area of quite a few square millimeters, and on that area there could be 100 million or perhaps even a billion transistors. And therefore the component size, the size of an individual transistor in a modern computer chip, might only be tens of nanometers, where a nanometer is 1,000th of a micron, and a micron is 1,000th of a millimeter. So we're talking about of order 10 billionths of a meter for the component size that we can manufacture. And of course, anything made on that scale, we have to worry about what the world is made of. We can't just assume that we can take a piece of silicon, cut it in half again, cut it in half again. We can't keep on going to infinity and assume that it'll still have those same properties. We have to think about whether there's a finite limit to how much we can zoom in to the structure of matter. So we can ask the question, what's the world made of? And how can we tell what the world is made of? And what clues do we have that tell us what stuff is made of? When we look around us and we pick up a rock or we look at a piece of wood, how can we tell what's going on? Well, one attitude is to take the Aristotle view and just say, well, everything is made of earth, air, fire and water. That's a nice, easy approach. It's only a question of just juggling the amounts of each of those four elements, and that will create everything we see around us. A nice idea, but just a little bit too simplistic, as the bottom line is, it doesn't work. Along comes scientists a few centuries later. Galileo was the first to really say we should be thinking about experiments. We should be trying to find out what the world is made of by using quantitative experiments, not qualitative intellectual arguments. In other words, we shouldn't be asking what should happen if I try something. We should be asking what actually happens. In other words, if I've got two cannonballs of different mass, it doesn't matter if we argue about what should happen if I drop these two objects. What we should be doing is measuring and finding out what happens to those objects. Then we'll find out something about the world around us. And Newton took this to the next level a few decades later, and he established the things we're all, I'm sure, familiar with. His laws of motion, his law of universal gravity. He understood, or at least made great inroads into understanding the nature of light. And he established what we now call classical mechanics, sometimes Newtonian mechanics, to distinguish it from our understanding of the world as it stands now, where we've got a much better idea of the nature of atoms and molecules and everything in the subatomic realm. So Newton figured that the universe was clockwork. He knew about the planets going around the sun. He understood the concept of gravity. He knew that's why the planets are in orbit around the sun. The orbits aren't circular, they're elliptical from the measurements made by Kepler et al. And so, as far as Newton was concerned, if we know where Jupiter is now, and we understand how it's moving and how it's being pulled by the sun, then we can understand where Jupiter is going to be tomorrow and next year and in 1,000 years. And if we want to, we can wind the clock backwards and we can calculate where Jupiter was 1,000 years ago. We can calculate where it was at the birth of Christ, for instance. If we want to know, was it the Star of Bethlehem, we can calculate because the universe is clockwork. Well, fine, that works reasonably well at the sort of scales we're talking about. But when it comes to understanding the nature of matter, what clues do we get? Well, if we look at snowflakes, they're all different, but they all seem to have a particular symmetry. They all have this characteristic six-fold symmetry. So that must be telling us something about not what's going on in outer space, but what's going on in inner space. It must be telling us something about whatever they are, the building blocks that make a snowflake must somehow want to generate six-fold symmetrical shapes. So does that mean the little Lego bricks that we're looking for, the building bricks of matter, are these little Lego bricks six-sided? Because otherwise, how do we explain snowflakes? But we look at other materials and we find indications that, well, maybe the building blocks that we're looking for are different shapes. And there are some crystals where some materials that show a crystalline form, and in this particular case it shows this sort of cubic or cuboid form, and again we might assume that these things must be made of building blocks that are themselves cuboid in structure, so that we can imagine them making up these larger structures. But how could we possibly explain something like this? This wasn't known to the ancients. This is only a relatively recent discovery in the last few decades. But it's possible for crystals to exist in this form, this icosahedral form. So we can perhaps imagine building blocks, whether they be square or whether they be hexagonal, making up regular crystals. But what possible shape of building blocks could we have that would explain why we get an icosahedral structure such as that shown in the picture there? So all in all, the macroscopic shape of materials, and in particular these sorts of crystals, and the shape of various materials must be telling us something about the underlying structure. And that's why a number of scientists across quite a few centuries started the task of, well, this is giving us clues, let's start digging and find out what the world is made of. Most of the progress was made over this time from 1600 to 1900. Way out on the left there, in the wrong position, is Democritus. He should be way over at sort of close to zero, because he was saying maybe there is a limit, maybe there is this fundamental building block which we call atoms. Indivisible, there's nothing smaller than this building block. And that idea was taken through these 3 centuries by a number of key players. I'm not going to talk about the history of how these individual scientists came to determine that atoms exist, but just for a little bit of fun, can we recognize who these people are? I'll go through them one at a time. We've got Boyle, I'm sure you recognize Newton, and then we have Lavoisier, then we have Dalton, then we have Avogadro, then we have Maxwell, and then we have Boltzmann. So their pictures are placed, roughly speaking, at the time point at which they made their largest contributions. In this period, a lot of it was chemistry. A lot of it was, if we react material A with material B, we get a different material C, and the ratio of what we get when we find, if we boil it, does water come off? If we can separate it into its constituent parts, what do we find? Looking at relative weights of reagents and the result of reacting materials together, different chemicals together, it was determined that there are fundamental small packages that seem to explain how different things react. Eventually, these were come to known as atoms. During the 1800s, there were a couple of key observations that helped us understand the world around us: the nature of particles and the nature of waves. In the 1800s, Young did experiments on the nature of light and showed that two light sources could produce a result in which interference is visible. And interference is a known wave phenomenon. We can see it, for instance, in water waves. So it's something that we can readily establish in the macroscopic world. So in the early 1800s, it was established that light was a wave. Back in Newton's day, the jury was out. People argued it was a particle, people argued it was a wave. But in the early 1800s, the experiments by Young proved that light behaves in a wave-like manner. Later on in the 1800s, J.J. Thomson established that a negatively charged particle called the electron exists and is part of the building blocks that we're looking for. They're part of these elusive atoms. It can't be that an atom is an electron because electrons are negatively charged. And it is known that the macroscopic world is neutrally charged because we don't go flying away from each other because we're all positively charged or all negatively charged. In general, we are electrically neutral. So if Thomson has discovered a particle, all of which are negatively charged, that means there must be at least one other particle we haven't found yet, which is positively charged, and we don't know how many, but presumably these positive and negative particles make up the atoms that we're looking for. So as of 1900, we have this picture: light is a wave, electrons are particles, and all we have to do now is discover what those positive particles are, and we've probably got the whole understanding of the nature of matter sorted out. Unfortunately, after 1900, basically everything went out the window, because not in the entire century, but only in the first 3 decades of the 1900s, everything was turned on its head. Again, here are the key players. I'm not going to go through the history of exactly what each of them did. Firstly, let's just establish who these are in this particular rogues gallery. Perhaps you recognize some of them. Starting from the left, we have Becquerel, and then we have Planck, and I'm sure you recognize Rutherford and Einstein. And then we have Bohr and de Broglie and Heisenberg and Schrödinger. Again, their pictures are placed, roughly speaking, where they made their major contributions in these decades. And what was established during these 3 decades are the following little snippets of understanding the nature of atoms and the nature of how matter is made of atoms, where what I'm going to show in red at the bottom doesn't necessarily relate directly to each person above. But we have the discovery of radioactivity, the establishment that light is a particle, the discovery of individual atoms and the atomic nucleus, the fact that probability is an important element, that electrons are waves, and then we have the building of quantum mechanics itself. And if we have a look at a few of these particular points, see here at the start of the 1900s, 1 century earlier, it was established that light was a wave. But now Planck comes along and says light is a particle. So a certain element of confusion there. Having established that the atom exists with a positively charged nucleus, eventually we came to call these positive particles protons, but all that matters is the nucleus is positive and the electrons are negative, and hence all atoms are neutrally charged. But one of the most important observations was that probability is an important element of discussing the nature of atoms and the nature of how atoms make up the world. It is not clockwork. It is not Newtonian. This is why we distinguish classical mechanics from the physics that we're now describing, which ultimately became known as either quantum theory or quantum mechanics. And notice here another experiment, another set of observations, that electrons that a century earlier were established by J.J. Thomson to be particles, it's now indicated here that electrons are waves. So Heisenberg and Schrödinger were the principal architects who tried to draw together all of this conflicting information that was established from previous centuries and in these 3 decades to try and build a mathematical construct, a mathematical theory, which explains why we get this particular behavior. And at its heart was the nature of matter, whether we call that electrons and protons or atoms and molecules, and the nature of light, and establishing that they both behave as sometimes like a particle and sometimes like a wave, so-called wave-particle duality. We cannot say that this object is definitely a particle. We cannot say this object is definitely a wave. The behavior of these entities seems to change almost day by day or hour by hour. And I'll discuss the nature of the problems establishing how we deal with something like that in just a moment. So Heisenberg and Schrödinger are essentially the architects of what we now call quantum mechanics, which has been with us now for about a century. So we think we understand what an atom is. We could say, well, yes, we understand what an atom is. Of course we do. We've known about them for over 100 years now. It's an object which has got a positively charged nucleus, and buzzing around it are negatively charged electrons. And there's the same amount of positive charge in the middle as there is in the negative charge of the electrons buzzing around. But this particular picture, which is quite a popular picture, and it's possibly the one we all have in our heads when we think, what does an atom look like? Well, that's sort of okay, but one of the principal problems with a little artist's impression like this is that it doesn't show us, it doesn't tell us that all the electrons have different energies. This particular picture makes it look like all the electrons are the same. They're all the same distance, they're all going around the nucleus at the same speed. But that's not how atoms work. All the electrons in an atom will have different energies. So perhaps a slightly better picture is to think of them in what you might think of as orbits. We don't tend to call them orbits in atoms, but let's stick with that language just for the time being. So at the top there's a two-dimensional picture of how electrons are arranged in an atom that has quite a few electrons in it. The top picture is two-dimensional, a little bit like a solar system, and we know that atoms are actually three-dimensional, so really it ought to be a three-dimensional picture, a bit like the shells at the bottom, which have been cut in half to reveal this sort of nested set of shells, or Russian doll model of shells within shells within shells. But the top picture makes it a little easier to draw, especially on a sheet of paper. So it's a little bit like a solar system, but notice there's a lot of differences. Well, yes, there's a big heavy nucleus in the middle, just like there's a big heavy sun containing most of the mass of the solar system at the centre. But one of the differences are that you can see that if you think of the objects here going round in orbits, you can see that there's 2 electrons in one orbit, and then there's 8 in the next, and then there's 18 in the next, like a string of pearls. It's not like one planet per orbit, which it is in the solar system. So it's rather different, and it's rather dangerous to start thinking about an atom as simply a solar system of electrons buzzing around the central sun or nucleus. The power of the idea of there are 2 electrons in this orbit and there are 8 in this and there are 18 in that. The numbers come out of quantum theory that Schrödinger and Heisenberg put together. I'm not going to go through the details of how we generate those numbers, but the numbers are sacrosanct. We can't say, well, maybe it's not 2, then 8, then 18. Maybe some of the time it's 3 and then 7 and then something else. No, it's always 2, then 8, then 18. And that explains the periodicity that we see when we look at the characteristic properties of various elements in the periodic table. The elements are arranged this way. Perhaps you remember it from school, perhaps you've forgotten all of this stuff, but the elements are arranged in this way because they get heavier from top left to bottom right, and any elements in a given column will have similar characteristics. So for instance, on the right hand side, helium and neon and argon and krypton and xenon are all gases, and they all have very similar properties in this column. And similarly, if we look at the left hand side, lithium and sodium and potassium and rubidium and cesium are very reactive metals, and they have, again, very similar properties to each other. And the similarity is because of the nature of how these electrons sit in their orbitals, with particular numbers of electrons in each of these shells, if you like, each of these electron shells. So it's dangerous to think of an atom like a solar system, because it basically is not, and it does not behave the same way as a solar system. It's tempting to say, well, it's a bit like, either planets in the solar system, or maybe it's a bit closer to a lot of a constellation of satellites buzzing around the Earth, in the sense that the picture we have on the left is the popular picture of electrons in an atom, and the picture on the right is a whole load of satellites buzzing around the Earth. But that's equally wrong, mainly because both a solar system and the idea of satellites around the Earth make you think that everything is just operating by clockwork, according to the rules set down by Newton. And that is the basic problem. We should be thinking about the probability of something happening. We shouldn't be asking, how does the electron move around the nucleus? How fast is it going? And if I know where it is now, can I work out where it's going to be a microsecond later, or a microsecond after that, or a microsecond after that? We should be talking about the probability of, if we make a measurement, what is the likely outcome of that measurement? If I want to measure where is an electron, if I want to measure how far is it from this electron to this nucleus, then we can calculate the probability of getting a given answer. But we cannot calculate absolutes. We cannot predict the future. We can only calculate the probability of something being likely to happen. So this particular set of pictures here, these grayscale images, some of which are bright and some of which are dark, are telling us the likelihood of, if we were to measure the distance from the electron to the nucleus, let's take this sort of figure of 8 dumbbell on the left hand side. The nucleus is in the middle where we can't see it, and these grey clouds are telling us the probability of finding the electron at a given distance from the nucleus. The darker the cloud, the less likely we are to find the electron at that location. The brighter the cloud, the more likely we are to find that electron at that location. But at no time can we say we are sure. We can only say this is the most likely, or the probability is this much. And these 8 pictures you can see here are just different electrons at different energies in different atoms, to show you that these probability clouds, if you like, if you want to think of them that way, can be very different from each other and quite complex in their own rights. So how do we describe atoms? Well, we can try using words if you like. But if we use words like particles and waves, we've already established that an electron is, strictly speaking, neither a particle nor a wave. It's sort of both. And light is sort of neither a particle nor a wave, but is both. And if we talk about electrons in orbits, well, they're not in orbit around the nucleus in the same sense that the Earth is in orbit around the Sun. And so we can use words, but we have to be very careful because those words don't necessarily mean what we think they mean. We can't use ordinary communal garden language that is useful in the macroscopic world. We can't assume those same words apply when we're dealing with the microscopic world. So if words aren't very good, then should we just be using pictures? But we know pictures aren't very good because a picture always makes it look like a sort of clockwork system. And even a picture which recognises the fact that we should be dealing with probabilities rather than anything else, that's still only a pictorial representation of one aspect of how atoms behave. So if words aren't ideal ways of talking about what atoms are, and pictures aren't ideal either, how should we describe atoms? Well, you could argue there's only one way to do it properly. And I'm afraid to say that is maths. That is the only way we know of that accurately describes the behaviour of atoms and molecules and everything else on the smallest of scales. So what Schrödinger and Heisenberg did effectively was write out the mathematical construct, the mathematical set of equations that are required to allow us to calculate anything we want to calculate. Of course, if we want to teach quantum mechanics to anybody, including students at university, we can throw the maths at them, fine, but we have to be able to interpret what the maths is telling us, which means we need to describe things using words and quite often using pictures, because we humans, generally speaking, understand things better if we have a picture in our heads. We're fairly visual animals. If we have a picture in our heads, it helps us understand what it is we're dealing with. So maths is the core of how we deal with atoms. Words and pictures might help us back that up. Unfortunately, the maths isn't easy to deal with. It is not primary school level maths. It is the sort of maths that students have to deal with if they want to understand the quantum world. They have to learn the maths. They have to learn how to apply the maths to the particular problem they're trying to deal with. And they need to learn how to interpret the mathematical solutions that they are dealt with. And as you can see from this little snapshot of possibly it's probably a mix of first and second and possibly even third year quantum mechanics at university level. Writing the maths down is sometimes easy. Figuring out what it all means can take an awful long time. Heisenberg said, "We wish to talk about the structure of atoms, but we cannot talk about atoms in ordinary language." In other words, ordinary language is not built to do that. Ordinary language, natural language, has evolved so that one human can talk to another about, is it safe to go outside the cave? Is there a lion about to eat me? Where are we going to get our next meal from? Natural language is built up so that humans can socialize. It's not designed to talk about atoms. Would it be better to use words that don't already have some meaning or some preconceptions? Rather than talk about electrons orbiting and spinning in the atom, would it be better to say the slithy toads did gyre and gimble in the wave? Because those two red sentences carry exactly the same amount of information. They're both meaningless unless you say, what do we mean by electron? What do we mean by orbit? What do we mean by spin? What do we mean by atom? You effectively have to define each of those terms before the sentence makes any sense whatsoever. And by reusing a word like orbit, you instantly think, just like the Earth orbits the Sun. No, it's a different type of orbit, so let's perhaps not use that word. Too late. We've been using that word for the last 100 years and it's impossible to change. So we still talk about the spin of an electron, even though it's not the same as the spin of the Earth, for instance. But we're stuck with those words because we've been using them for too long now. Bohr said, everything we call real is made of things that cannot be regarded as real. So I believe solid things are real because my senses tell me they're real. And yet they're made of atoms and molecules. And it is not obvious what we mean by real when we're talking about ghostly things that behave according to the rules of mathematics, but are not billiard balls in the Newtonian sense. So we have statements like this. What do we mean by reality? How can we understand the nature of the world around us when it seems to be made of very ghostly things that obey certain mathematical rules, but not Newtonian mechanics? Schrödinger said atomic physics has shown that atoms have no meaning, but can only be understood in experimental measurement. What he meant by that was quantum mechanics is a theory, it's a construct which allows you to calculate essentially anything you like. In other words, if I've got a cloud of hydrogen up in space and I excite it by giving it energy, what colours are going to come out of that cloud? Quantum mechanics will tell us if you excite atoms or molecules of hydrogen, the electrons will behave in this way and you will get light of this wavelength, or this colour if you like, coming out. Quantum mechanics tells us how things behave, and yet it's difficult to reconcile that with the fact that when we get down to individual atoms, it's not obvious what we mean by individual atoms or individual electrons or individual subatomic particles. And yet the mathematical theory that was constructed by Heisenberg and Schrödinger allows us to calculate essentially anything we like. And generally speaking, when we do that, we get the right answer. When we compare it with what hydrogen actually does when it's out in space and glowing, we find the calculation gives us exactly the right prediction for expecting light to be emitted at 656 nanometers or whatever. I don't like it. I'm sorry I ever had anything to do with it. Again, for somebody that 100 years ago built quantum theory, the fact that he says I don't like it is a reminder that even the people who built it found it difficult to understand why it worked. Why is it that atoms behave with mathematical predictions that tell us about the probability of events occurring? How do those atoms know how to behave? Why do they obey these rules? And why don't they obey Newtonian mechanics? Part of the problem with understanding quantum mechanics is that it does not agree with common sense, mainly because common sense is something that we have put together to understand the world around us at the scale of humans, at the scale of millimeters or meters or kilometers, not at the scale of atoms. So some of the ways that quantum mechanics disagrees with common sense. Atoms, and that means pretty much anything, all particles in the universe are unpredictable. In other words, we can only talk about the probability of an atom or a molecule or a collection of molecules having a particular position in space or a particular speed or a particular energy. We cannot ever say this object is quite definitely at this position moving with this speed. The only thing we can say is if we were to measure it, then the probability of getting this answer is this, and the probability of getting that answer is that. We can calculate the probabilities of getting answers to any problem we want to set, but we cannot know with certainty anything. It also means atoms do not have a finite size. We tend to think of atoms as small, but what do we mean by small? Because if we ask the question, how far is it from the electron to the nucleus of an atom in a hydrogen atom? Well, the answer could be anything. It's most likely that the electron is within a nanometer, a fraction of a nanometer of the nucleus. There's a nucleus, an electron that we can imagine, as it were, in orbit around that nucleus. But if we ask the question, if we were to measure the distance from the electron to the nucleus, what are we likely to find? The answer is we're most likely to find the answer is a fraction of a nanometer. But the answer might be 2 nanometers, or 10 nanometers, or a micron, or a millimeter, or a meter, or a light year, or a million light years. There is no point at which the probability that the electron to nucleus distance, there's no distance at which it goes to zero. It gets smaller and smaller and smaller and smaller the further we go. And it is ridiculously small if we go just a few nanometers away from the nucleus. Yes, it's small, but it's never actually zero. So when we ask the question, where could the electron be? The answer is, well, it might be anywhere. So the idea that an atom is only this big, smaller than a nanometer, what we really mean is it is most likely that the electron is within a nanometer or so of the nucleus. And we ignore the fact that actually it might be further away than that. So it doesn't agree with common sense, but that's the way quantum mechanics works. Third way in which quantum mechanics doesn't agree with common sense. Atoms can be in two states at the same time, which is like saying an electron can spin clockwise and it can spin anti-clockwise, that's fine, but it can do both of those at the same time. If I said the Earth is spinning as seen from above the North Pole in the clockwise sense and in the anti-clockwise sense, both at the same time, that clearly makes no sense whatsoever. And yet it would appear that atoms can exist in this state and in that state at the same time. Even those two states appear to be quite distinctly different from each other. And again, that just doesn't agree with how we think the world ought to work. And Einstein summarized it like this: common sense is the collection of prejudices acquired by the age 18. In other words, as children, we try and work out how the world works by observing it and learning from our parents and from others. And common sense is simply the collection of ideas that we have. If I were to pick up this computer mouse and drop it, I think it will fall, because at no time in my life have I ever picked up a computer mouse and let it go and found it drifted up to the ceiling. Every time I've done that, it always falls to the floor. So I think that's the way things always should work. And that's what common sense is. Common sense is just, I have seen this happen a zillion times and therefore I think it's always going to happen that way. But when we look at atoms, we cannot use our knowledge of how the macroscopic world works to predict how atoms are going to work. Einstein never really liked this idea of probability dictating the way the universe works. Einstein didn't necessarily think the universe was clockwork, but he thought we were missing something. He didn't like the idea that when an electron, let's say, or when an atom, let's say we've got a radioactive atom, when is that radioactive atom going to decay? That's determined purely by random chance, by probability that it will or won't decay. Whereas Einstein thought, no, there's got to be some underlying reason why. It's not just a question of the toss of a coin. He famously said, God does not play dice. God is subtle, but he is not malicious. Einstein believed that this idea of probability was not the correct one. And when he said God does not play dice, Bohr disagreed with him and said, stop telling God what to do. That is the way the universe is. The universe is built the way, according to quantum theory, tells us. And apparently the universe is built according to the rules of probability, not according to the rules of clockwork universes. Let me go on to 3 aspects of quantum mechanics that gives you an idea of just how weird it can be. The 3 things I'm going to talk about are the fact that order matters. I'm going to talk about Schrödinger's cat, which you may have heard of, and I'll be talking about how we can use quantum mechanics to build a microscope that allows us to see atoms. So firstly, order matters. What I mean is, in algebra, A times B is the same as B times A. 2 times 3 is the same as 3 times 2. The answer is 6. It doesn't matter which way round you do the multiplication. But in quantum mechanics, the order in which you do things does matter. So something that's represented by A times B is not the same as something that's represented by B times A. Now, who cares? Okay, so the order matters. So let's take an example and ask ourselves, if the rules of quantum mechanics did apply to the macroscopic world, how weird would it be? Okay, let's imagine we've gone to Africa and we've got 4 types of animal out on the Serengeti. Okay, there's probably more than 4 out there, but let's just assume that we've just got these 4. The top pair of animals here are carnivores, a lion and a vulture. And the bottom pair are vegetarians, a waterbuck and an ostrich. But we could take those 4 animals and we could think of them as 2 different pairings. We could think of it as, well, the left-hand pair have got 4 legs, the lion and the waterbuck, and the right-hand pair have got wings, the vulture and the ostrich. Yes, I know the ostrich can't fly, but it still has wings. It still counts, okay? So, if order matters, let's do a little experiment. Let's pick 2 out of the 4. Out on the Serengeti, we have 4 sets of animals. What we're going to do is take 2 of them and corral them separately. We're going to go out there in a van and capture them and move them to one side. So let's pick 2 out of the 4. For instance, take an example. Let's pick the vegetarians. So we're going to go out there and we're going to pick the vegetarians and put them to one side. We're now saying, right, we've got 2 animals, the waterbuck and the ostrich. Now that I've selected those 2, I'm going to make another selection from the set of animals that I've got, just the 2 in this case. I'm going to pick again. This time I'm going to pick out the 4-legged animals. So if I've got waterbuck and ostrich, and from those I pick the 4-legged animals, I would expect to be left with just the waterbuck. If we do this according to the rules of quantum mechanics, we end up with a waterbuck and a lion. Even though we've selected out the lion because we started with vegetarians, and then we said from the vegetarians, let's pick the 4-legged ones, the lion has somehow got back in. It's as if the second choice we made somehow overrules the first choice we made. And if we do the same again, but this time let's pick in a different order. This time let's pick the 4-legged animals first. Let's go out there, let's shoo away the ostrich and the vulture, and we're just going to pick the lion and the waterbuck and put those to one side. And then we're going to choose from that pairing, we're going to pick out the vegetarian of those 2 4-legged animals. What we expect to do is to pick out just the waterbuck. But what we actually find is we're left with a waterbuck and the ostrich, even though we had eliminated the ostrich at the first pick because we picked 4-legged animals. It doesn't make sense. That's not the way things work. If we corral animals on the Serengeti, or whether we pick socks out of a sock drawer, that's not the way the world works. But that is the way the world works on a quantum mechanical level. The weird world of the very, very small does behave like that, and it makes no sense, and that's part of the problem with trying to understand quantum mechanics, is because we can't use common sense to tell us when we're getting the answers right. The second example is Schrödinger's cat. So let's kill a cat. Oh, don't worry, we're not actually going to kill a cat. This is a thought experiment that Schrödinger came up with, and he said, let's imagine, not a real experiment, let's imagine putting a cat in a box. We're going to put a cat in a box and we are going to take a radioactive element, and over a certain period of time there's a 50-50 chance that that radioactive element is going to decay. And that produces a blip in the Geiger counter which goes into this box, and this box sends a signal to this robot with a hammer to smash the cylinder of poison, and that will then kill the cat. So inside this box, we are setting up an experiment in which over a certain period of time, there is a 50-50 chance the cat will be dead or the cat will be alive. The point is that Schrödinger, shown here at the top, is going to put the cat in the box, set up the experiment, and then close the box. After the experiment is done, without opening the box, what state is the cat in? Well, according to our understanding of quantum mechanics, the atom, which we think of as either having decayed or not, is actually in both states. Just like the electron can spin one way and spin the other way at the same time, the atom, the radioactive particle, will have decayed or not decayed, and both of those states will exist at the same time. It will be in both states. But if the fate of the cat is linked to the fate of that radioactive particle, that means the cat must be both dead and alive at the same time. Now, of course, if we open the box, we will find either an alive cat or a dead cat. We will never be able to see a cat that is both dead and alive. But the point of Schrödinger's experiment, the thought experiment, is that for as long as the box remains closed, the cat must be dead and alive at the same time. And it's only when we open the box and make a measurement of the state of the cat that the cat becomes dead or the cat becomes alive. Up to that point, the opening of the box, it's both. It is not a question of our ignorance. It's not a question of, well, the cat is one or the other and we don't know which until we open the box. No, quantum mechanics says it is in both states. And then when we open the box, we make a measurement and the cat becomes dead or the cat becomes alive. And the idea of Schrödinger's cat was Schrödinger's attempt to point out that things that behave reasonably sensibly on an atomic scale, if we then think about the consequences of that on the macroscopic scale, we end up with a logjam where we hit common sense again, and we have these problems of how can quantum mechanics be right if it tells us that we have a cat which is both dead and alive at the same time. And the answer is we haven't resolved that paradox. It's still called a paradox. Whether it is a paradox or not, it might simply be our lack of understanding. Or it might be that there's something wrong with quantum mechanics. But quantum mechanics has done such a good job up till now, we don't think it's actually that. So how do we know quantum mechanics is right? It's been around for 100 years, but why do we put so much store in it? Well, basically because it's a theory. Like any other theory, you try and test it to see if it's right or not. And for the last 100 years, quantum mechanics has been making predictions and we've been testing those predictions. And so far, nothing has proved it wrong. In other words, every time we're able to do a calculation in quantum mechanics to predict something, that prediction has always been correct. We've never yet found a situation where we observe something in the universe and quantum mechanics tells us it shouldn't do that. It should be something else. So far, whenever we've done a quantum mechanical calculation, we have not been able to prove that calculation wrong. So after 100 years of trying, it looks like this theory does indeed work. Well, the other reason why we believe it is that quantum mechanics not only gets it right every time, in a sense, it also makes predictions that Newton quite definitely gets wrong. There are certain situations where classical mechanics, using Newtonian mechanics, gives us a very clear prediction of what we would expect in a given experiment. And there are circumstances in which Newtonian mechanics gets it wrong and quantum mechanics gets it right. In other words, we absolutely need something beyond Newtonian mechanics, and so far quantum mechanics has been the saviour of getting these calculations right and has never yet tripped up and indicated to us quantum mechanics is wrong, we need something else. So we don't know it's right, but so far, after 100 years, we have found nothing better to explain how the world works. Let me finish with the idea that our knowledge of quantum mechanics can allow us to build a microscope that can effectively see atoms. It's called a scanning tunneling microscope. In the 1980s, it was a crazy idea, but since then, for the last 40 years or so, there are, I don't know how many thousands of these microscopes around the world. Every university will have one. Some schools have them. And they demonstrate quantum mechanical principles. If you take a sharp tip of metal, represented here by the red atoms, which is just the very tip of, if you think of it as a very sharp needle coming down to a surface, and again, it's a big surface, we're just representing that by a few atoms in blue here. And they're separated by a small distance d. If we apply a voltage between the two, no current will flow according to classical mechanics. The circuit is open, the circuit hasn't been closed, and you would have to touch those two together to get a current flowing. But quantum mechanics says a current flows even if there's a gap there, which disagrees with classical mechanics. So we can build ourselves a microscope by making a sharp tip, bringing it close to a surface and measuring how much current flows. And we can either move the tip horizontally across the surface, in which case the distance d that you see here on the left hand side, you see these distances change if we move strictly horizontally and our surface is slightly rough, then we'll get different distances and hence we'll get different currents flowing. What we actually tend to do is move the tip up and down to keep this distance fixed. In other words, we move the tip as it scans across the surface, we move the tip up or down so as to maintain a given current which maintains a given distance. In which case the tip, even though it's not touching the surface, will effectively map out the topography of the surface. And it will do this with such precision that even if d changes by less than the diameter of an atom, the change in the current will be large enough to measure. That's a prediction of quantum mechanics, and when we build one of these things, lo and behold, we find that yes, we can measure changes to the separation of the tip and the sample, even if they are a tiny fraction of the diameter of one atom. So you can see on the right hand side, if these are representing individual atoms, then d is going to change slightly because the atoms are, let's think of them as billiard balls for the purpose of this particular model. We know that they're not solid objects, but for the purpose of this demonstration, let's imagine them as little spheres. We can see d is going to change ever so slightly because we're going to be going over bumps which are effectively individual atoms. So if we measure the current at every point and then represent that as a shade of a colour or a 3D representation, we can get images of atoms. So there's a handsome individual standing in front of a scanning tunneling microscope. You can't see the microscope itself because it's inside a vacuum vessel which is designed to keep air out of the working environment. The vacuum vessel is evacuated down to about 10 to the minus 13 atmospheres, which keeps any oxygen or nitrogen or argon away from the surface so that we can genuinely study the surface that we're interested in, not the surface contaminated by air or CO2 or water vapor or anything else. And then we get images like this. This particular image is courtesy of some of my colleagues in the University of Manchester. This is the surface, you can get the scale from the bottom left hand side there, there's a 2 nanometer scale bar. This is the surface of rust. So what we're looking at here, these mountains, well, we know rust is made of iron and oxygen, so we know these mountains are either oxygen atoms or iron atoms. If I remember rightly, these are actually oxygen. But notice that they're not scattered over the entire surface. They are also not scattered at random. They're not scattered uniformly. They are quite definitely bunching themselves together into islands. These atoms want to be close to each other, but notice that these islands are arranged in a particular pattern on the surface. You can see, and you can imagine if this pattern was repeated, they're arranged in a sort of hexagonal pattern. And these islands are separated by much smoother regions. So in this case, the vertical scale has been exaggerated so that things that are actually quite shallow bumps are indicated more like large pyramids, for instance. But still, we can see that we quite definitely have individual objects, which we interpret as being individual atoms, and they are arranged on the surface in patterns that we can study to try and understand what does this surface behave like. Why is this the characteristic surface of rust? It happens to be a combination of iron oxides, Fe2O3 and Fe3O4, for those of of you who remember your chemistry, there are different phases of iron in this particular surface. And by being able to study individual atoms, we have a much better understanding of atomic reactions and molecular interactions between individual atoms and individual molecules. And we often see patterns. This happens to be a scanning tunneling picture of a metal alloy. And the scale here, again, the size of the image is about 10 nanometers. Notice that we see white blobs, which we interpret as either atoms or collections of atoms. Notice that some of these atoms are arranged in a sort of daisy pattern, and there are 10 of them if you count them. And every once in a while we notice, oh, look, there's a set of 5 there, there's a pentagon. That's not how we normally think of atoms tiling. We tend to think of that in squares or in hexagons in order to cover a two-dimensional surface. But here we have atoms in pentagons. And not surprisingly, that explains why it is that this particular metal adopts a crystal structure that looks like the one I showed earlier. Now that we understand the atoms can arrange themselves in pentagons, now we have a better understanding of why it might crystallize into this particular shape. Not only that, but if we look at the distances between atoms and make lots of measurements of the distance between these two atoms divided by the distance of those two atoms, for instance, and we do that for lots of pairs of atoms, we find a particular number keeps cropping up in this particular metal crystal. That ratio is this golden ratio of 1.618 blah, 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 blah. Why is that interesting? Well, it's interesting in its own right as to why the atoms should arrange themselves like that, but it turns out it's the same number that crops up in pineapples. If you were to measure how many scales do you have if you follow the spiral of a pineapple in one direction and the spiral of the scales in the other direction, if you take those two numbers and take the ratio, it comes out to be about the golden mean again, 1.6 something. And if you do the same with sunflowers, if you look at the head of a sunflower where you have these characteristic spirals, if you start from the inside and follow one particular spiral, you can count the number of seed heads, but you can do the same in the other direction because there's another set of spirals going in the other direction. If you count the number of seed heads in one spiral and the other spiral, take the ratio, it comes out to be the same number again. So atoms might arrange themselves in the quantum world in a similar way that macroscopic objects arrange themselves in the macroscopic world. And people are studying these sorts of similarities, trying to understand what is the underlying reason why atoms at one scale and seeds at a altogether different scale of millimeters might behave in similar, or at least recognizably similar ways. The penultimate image I want to show is this one, which summarizes the degree of confusion as to what's going on in the quantum world. Here, the people who've generated this image have taken a collection of atoms and arranged them in a circle, a corral if you like. And so what we have is this image which is sort of like a mountain range and something inside that range of mountains. So it looks like we've got a whole load of individual peaks here. So the atoms in this corral appear to be behaving like particles. They appear to be behaving like objects separated from each other by a given distance, and they appear to be tiny little billiard balls, in this case exaggerated in the vertical scale. But what's going on inside the corral? Well, we don't seem to have a little collection of dots in here. It looks a bit like we've got ripples in a pond. If you had a collection of water here and threw a stone in the middle, you would get the sort of ripples that we see here. So it looks like we've got particles around the edge, but we have waves in the middle. But this is all the same stuff. Are we dealing with particles or are we dealing with waves? In one image, it seems to be telling us we're dealing with both. And depending on how you've arranged the atoms, depending on what the electrons are doing, they might appear like particles, they might appear like waves. So one image gives us this essence of wave-particle duality, the fact that we can't really separate those two sets of properties. If quantum mechanics hasn't profoundly shocked you, then you haven't understood it. Or as I sometimes say to my students, if quantum mechanics hasn't shocked you, you haven't been paying attention, because it should shock you, because it is so different from common sense. Everything you've learned up to the point where you learn about quantum mechanics essentially has to be thrown out of the window, and you have to relearn what makes sense and what doesn't make sense. One of my favourite quotes from Einstein, the penultimate quote of this talk: the most incomprehensible thing about the world is that it is comprehensible. Yes, it's weird. Yes, we don't understand all of it, but we can make sense of it. The fact that quantum theory exists, it's a theory which does make predictions, which appears to agree with reality. Some people think it's incomplete. Some people think there's something going on under the surface. But the fact is, we have a theory for which 100 years it's given us the answers we need. And we don't always understand why. Some people say, well, quantum mechanics works. Who cares why it works? Let's just use it as a toolkit. The name quantum mechanics implies that, yes, it's a toolkit. It tells you what you need to do. And some people have encapsulated that in the wonderful expression, shut up and calculate. In other words, don't bicker about why it works. Just use it as a toolkit because it gives the right answers. If you want to know what is the wavelength of hydrogen light, you can calculate it using quantum mechanics and you get 656 nanometers. And that's what you want, a toolkit that allows you to do calculations and get answers, preferably answers that agree with the real world. So we may not understand everything, but it is not a state of confusion that we would call incomprehensible. It's weird, it gives results that we have to think about, but it is comprehensible. And that is perhaps the most surprising thing at all. The universe does not owe us anything, and yet we, thanks to evolution, are able to understand these things. Let's finish with this image, not one of mine. It's an image of carbon atoms. Notice the scale. It's not even 1 nanometer on a side. It's 850 picometers from one side to the other. And we're looking at a dozen or more atoms of carbon. If we think about the scale, depending on the screen or the laptop on which you're looking at this, if we imagine how big would a grain of sand be if we're looking at this magnification, well, a grain of sand would be about the size of the moon. That reminds you of just what scale we've zoomed into in order to see what we interpret as individual atoms. And whenever I see an STM picture and I'm looking at atoms and I realize we're looking at such a tiny aspect of even a microscopic speck of dust, I always remember William Blake. To see a world in a grain of sand, and a heaven in a wild flower, hold infinity in the palm of your hand, and eternity in an hour. Thank you all very much.